Okay, so welcome back. And so today we're going to cover the next topic, which is measures of relative position. Okay, so here we go. So this is measures of relative relative position. Okay, so now, what do I mean by relative position? I mean comparing values. So where does one value lie compared to another value? So relative position, ranking. So that's another, so think of ranking. So if I rank individuals, like for example, how well somebody does on an exam, or a standardized test, you know, if I want to compare how one person did with the rest of the population, then that would be a ranking situation, right? So that would be relative position, right? How does one person perform relative to everybody else, okay? So we're going to talk about, in this video, things like percentiles, deciles, quartiles, and then one particular one value that is going to be new for people who are in a stat course is going to be the Z-score, and that's what we're going to start with. So the idea of a Z-score. And since we talked about last time in measurements of variation, we talked about the standard deviation, and we talked about the empirical rule, if we know that the distribution is bell-shaped and symmetric. Well, we can then say, okay, how does one value compare to another value? What if we have two different populations and they're both bell-shaped and symmetric with different means and different standard deviations? Well, if I just throw out a value, right? Let's say I'm talking about the weights of Angus cows, right? And I give you that they're normally distributed or they're bell-shaped and symmetric, and I give you the mean and I give you the standard deviation of that distribution. And I just give you a random weight, okay? And then I take the weight of another group of cows. Let's say, I don't know, roan cows, right? And I give you their distribution, right? You know, it's bell-shaped, symmetric, with a mean and standard deviation. And I just randomly pick a cow weight from each one of those, and I give you a weight of the Angus cows, and I give you a weight of roan cows. Well, then the question is which one weighs more relative to its own population? Or which one's more extreme of a value, proportional to it or compared to the rest of its population? Well, it's going to be very difficult to discern that just by looking at the numbers, especially if they have very different means and standard deviations. So this is where the Z-score comes in. And what the Z-score is, it's a standardized score that allows us to do an apples-to-apples comparison. Right now, with the example I gave you with two different cows, so roan versus Angus, and I just give you two individual weights, I'm not going to be able to compare which one's heavier with respect to its population because it's an apples to oranges comparison, right? I have to consider how far each value is from its mean and what the standard deviation is, right? So if I was able to figure out, well, how many standard deviations, remember that from the last video, if I can say, hey, how many standard deviations is each weight corresponding to its own population, then if I was able to discern that, then I could say, hey, then I can do an apples-to-apples comparison, because if I know how many standard deviations this weight of this roan cow is compared to its mean and standard deviation, and I know how many standard deviations the weight of the Angus cow is with respect to its mean, the mean of its population with its standard deviation, then I would be able to immediately tell you which one is heavier with respect to its population. That, my friend, what I just described to you, is the Z-score. That's what the Z-score is going to tell us. It's going to tell us how many standard deviations above or below the mean a particular value is. And so that's what we're going to start with. So the definition of a z-score. So the z-score tells us how many standard deviations an observed value is from the mean. Okay, that's the definition. Okay, so think of z-score as like a ruler, right? And you're taking this ruler based on the standard deviations and you're measuring how many standard deviations a particular observed value is from the mean. Okay? And so the z-score is the number of standard deviations. So if my z-score is 3, then I know I'm 3 standard deviations above the mean because it's positive. If my z-score is 1.28, then that means the observed value that I'm considering, that I'm looking at, is 1.28 standard deviations above the mean. And if I look at a z-score of negative 1.35, then that tells me that the observed value that I'm looking at is 1.35 standard deviations below the mean. Okay? So if it's a negative value, you're below the mean. If it's a positive value, you're above the mean. Okay? And that's what the z-score is. So here's the formula for a z-score. Okay? You get the z-score by first taking the observed value. So again, this is going to be a mantra you're going to want to memorize because it's going to come up many times in different forms, okay, depending on the context and the situation we're dealing with. So it's going to be observed value minus the mean divided by the standard deviation. That is the formula. So always remember in your head, over and over again, to get a z-score, all you have to know is take the observed value minus the mean divided by the standard deviation. The observed value minus the mean divided by the standard deviation. If you remember that, you'll always be able to figure out the formula. So the first formula we're going to start with, and this is going to change as we go on, but the first formula is just dealing with a data set of x values. Okay? So in this case, my observed value is going to be whatever x value I'm given in the problem or out in the real world. Okay? It's the value I'm considering, that I'm trying to get, that I'm trying to figure out how many standard deviations it is from the mean. So it's just whatever the observed value is that I'm looking at or given. Okay? So it's going to be x minus the mean, which is going to be mu, the population mean. And so remember, mu is the Greek letter that represents the population mean. And so it's going to be the observed value minus the mean divided by the standard deviation, which is just sigma. Okay? So that's our formula. That's the formula for the z-score. Okay? So we're taking distance. So think of it. We're taking the distance a value lies from the mean, and we're dividing it by the standard deviation to get how many standard deviations we are. Okay? That should make sense. Okay? Again, just think about measuring my distance here to the wall. If I use a ruler, I'm just basically subdividing how many rulers it takes to get to the wall. That's what I'm doing here with this formula. I'm taking the standard deviation and I'm dividing the distance up, seeing, hey, how many standard deviations does it take to get to my value? Okay? That's really all we're doing. Now that z-score is important because now I have a way to make an apples-to-apples comparison between two values within one population, or if I wanted to compare values, two values from different populations that are bell-shaped and symmetric. So one thing you have to remember is z-score only works when you're dealing with symmetric and bell-shaped distributions. If you're dealing with skewed distributions, we're not going to use a z-score. Okay? We'll cover that later. Right now, we're just going to deal with bell-shaped and symmetric. And later on, we're going to talk about a special bell-shaped and symmetric that comes up a lot, and that's normal. Okay? So this is the calculation for z-score. And again, all it tells us is how many standard deviations above or below a value lies. Okay? Okay, so let's look at an example here. Okay? So let's say we have an example, and we're looking at this table. So in this table, we're looking at two students, John and Ali, and they're from two different schools. Okay? And they wanted to find out who had the highest GPA, or higher GPA, since there's only two, higher GPA relative to their school. Okay? So now, they are on two different scales. Okay? So they're on two different GPA scales. Okay? So let's look at this table so we understand what's going on here. Okay? So here is the table. Here's a student. So here's John. And here's Ali. Okay. And let's look at GPA. So here's GPA. And his GPA is 2.85. And his GPA is 77. Very different numbers, right? Two different scales, okay? Think about ACT and SAT scores, right? That's another great example to use that we'll talk about later. It may not come up or will be talked about in class, but SAT scores, right? Comparing SAT versus ACT scores, right? If you take two different scores, two different tests, let's say you take both tests and you want to compare how did you do better on the ACT exam or did you do better on the SAT exam? Well, they're two different scales, so it's going to be very hard to look at just the two numbers and say, oh, I did better on this exam than the other one. Well, if we change them both to z-scores, then it's easy to see. Okay, so that's what we're going to do with these two, but this is GPA. Okay, so now here's the mean GPA for the individual schools. Okay, so here's the school mean GPA. Okay, just want to make sure I have enough room on the, okay, good. So, and then if I extend this out, okay, just want to make sure, okay, good. So if I extend this out further, then I also want to put in the school standard deviation. So you can look at these two schools as two different populations, right? So this is school A, right? And school B, right? For each school. So the school not mean, I don't want the mean. So now we're going to use a standard deviation. I'm going to abbreviate SD for GPA. Okay. So this is going to be the mean. So think of this as mu. So this is going to be mu, and this is going to be sigma. Okay? So think of John, this is going to be, let's say, mu1. Okay? And then for Ali, we'll call that mu2. So this is population 1, right? So this is population 1, population 2. School 1, school 2, right? Okay? So this is mu1 and mu2. This would be sigma 1 versus sigma 2, right? And so what's the mean GPA for this school? Well, let's say it's 3.0. And the mean for this school, based on its scale, is 80. And let's say the standard deviation for this school is 0.7. And the standard deviation for this school, GPA, is 10. Now, looking at these two observed values. Now, here's the thing. Here's the observed values. So these are x1, and this is x2. So this is John's GPA, and this is Ali's GPA. Okay? So now, think about this. If I just look at these two numbers, I'm not going to know who did better just by looking at those two numbers. It's going to be very difficult to figure out. Even if I'm going to divide and do it in my head, it's hard to say how many standard deviations from the mean this value is compared to this value. So, easy calculation, just make them both into z-scores. So here's how we're going to do it. So I'm going to calculate z1, and I'm going to calculate z2, and then we'll easily be able to do an apples-to-apples comparison. So what's z1? Well, this is going to be for John, right? So for John, it's going to be the observed value, which is x1, minus the mean, which is mu1, divided by the standard deviation, which is sigma 1. Okay? And so if I do that, I'm just going to plug and chug. So 2.85 minus the mean, which is 3.0, divided by the standard deviation, which is 0.07, or excuse me, 0.7. Okay? And so if I calculate this, let me get my calculator out. If I calculate this, I just do 2.85 minus 3 divided by 0.7, and I get negative 0.21. And for z-scores, only go out 2 decimal places. Okay, so just remember that, 2 decimal places. Most tables only go out 2 decimal places for z-scores. So this one here is going to be negative 0.221. Negative 0.21. That makes sense. Negative 0.21, or if you want to write it with 0 in the front, so negative 0.21. So again, it's negative because look at the numerator. The numerator will always tell you whether it's negative or positive. So it makes sense this is negative. So immediately, I know where this value falls relative to the mean. It actually falls below the mean. Okay, so this z-score, this GPA, is actually slightly below the average for this school. Okay, because it's negative. Remember, negative tells us it's below. Positive tells us it's above. Okay. Okay, so now, let's do the same thing for Ali. Okay, now let's take Ali's information and put it in there. So, again, we're going to take x2 minus mu2 divided by sigma 2. And remember, that's the standard deviation. So again, we're going to subtract off the mean, divide by the standard deviation. So again, we're going to do the same thing. So this is 77 minus 80 divided by 10. So notice this is also going to be a negative z-score because of the numerator. We're subtracting off a bigger number, so it's going to be negative. Okay, so now here's the moment of truth. So what do we get? We get negative 0.30. Let me make sure that I believe that's going to be exactly that. Yeah, so negative 0.3. So it's going to be negative 0.30 exactly. So now the moment of truth. So who did better? Who has the better GPA? Well, they're both below the mean, but which one is higher? Which one's closer to the mean in this case? So the one that did better is going to be the one that is smaller negative. So this one is higher than this one. So who did better relative to their school? John. Okay? Any questions? Now, so notice how if we were just looking at the numbers, it would be very difficult to see who did better. But as soon as you change it to a z-score, it's obvious. Okay, so that's how we can utilize z-scores to compare different numbers, different people, different subjects. Okay? Okay, so now, let's see. Percentiles. So the next topic we're going to talk about are percentiles. Percentiles is another way of ranking, okay? So, or excuse me, comparing values. And percentiles are extremely common. We use them all the time. I mean, just think about the ACT, SAT, when you're in school, they do all kinds of standardized testing, right? Schools want to know how they compare nationally to other schools, within their state, within their district, it's just to ad nauseum. I mean, to be honest with you, all the testing we do. So percentiles are very common, very useful, very easy to understand, right? And so the definition of a percentile. Okay, so let's start with the definition. So the percentile, let's move over. Let's start over here. So let's do percentile. Okay, so percentile. What is a percentile? The percentile represents the percentage of values, of data values, that fall at or below a particular value. So if I give a particular value, an x variable, like an x value, right, some data value, then whatever the percentile is would tell me, hey, what percentage of the data falls at that number or below it. Okay? Does that make sense? Okay, so what is it? It's the percentile, right? It's the percentage or proportion of values that fall at or below a particular value. A given value. I'll say a given value. That's what I'll say. I think that's better. Okay? And the way we denote a percentile is usually a P sub a piece of number. We'll say P sub n. Okay? Where n will go from 1 to 99. Okay? So let me explain why that makes sense and why we use that. Okay, so let me draw a diagram, and it'll make perfect sense after I do this. Okay, so let's take a normal curve, or a bell-shaped symmetric curve. Okay? So let's say we have this curve, and what I'm going to do, and this is exactly what we mean by percentiles, is we're going to partition the curve, right, or the data, right? It could be a data set. If I take a data set and I order it from smallest to greatest, or greatest to least, then I can partition it into 100 equal pieces. And that's what I'm doing here with this curve. Is a percentile means I'm partitioning the data. I'm cutting the distribution, the curve, into 100 equal widths, 100 equal pieces. Okay? So think of a histogram doing the same thing. Okay? So what I'm doing is I'm cutting the data, right? Where each one of these pieces is equal to or contains, okay, so remember the empirical rule, okay? Think of the empirical rule, right? So we had those partitions, right, based on the standard deviation. Well, think of it that the way we do a percentile is we're subdividing this interval into 100 equal pieces where each piece has an interval that contains 1% of the data. So I know that 1% of the data falls between these two values, and then I know 1% of the data falls between these two values, and so on and so forth. So each piece contains 1% of the data, okay? That's the idea behind a percentile. Because then what happens if I choose this piece right here, this cutoff, right? And let's say this is my x value right there. Well, a percentile means, hey, well, what percentage of the data fall at or below that value? So the big idea behind a percentile is, well, I just have to add up all of the pieces to the left, right? So the percentile tells me the percentage of values to the left, or below or at that value. So in other words, to find the percentile, I just have to add up all of the percentages to the left of the given value, okay? So if this is, let's say this represents the 95th percentile. Oops, I won't say that. Let's say it represents the 95th percentile, okay? So that means the percentage of values to the left of that x value would be 95%. So 95% of the data fall below that. So again, think of standardized testing. Let's think about the SAT score. If you got your results back and it said, hey, in math, you scored in the 95th percentile. That means of all the students that took the exam that day, you scored better than 95% of them. Or more to the point, that by definition, the 95th percentile means that 95% of the people, the students that took the exam on the same day that you took it, did as well or worse than you did. Okay, that's what we're talking about. Okay, so how would we represent the 95th percentile? This would be the same as just saying P sub 95. Okay, so again, we could just say 95th percentile or P95. The 95 represents the percentage of data that falls to the left or below that value, at or below that value. Okay, so with that in mind, that's going to help us explain or be able to figure out what the percentile is of a particular data set. So keep that in mind, the definition in mind, because we're going to use that to actually calculate a percentage, or excuse me, a percentile. Okay, so let's use an example. Okay, so let me see here. Let's see here. Let me see here. Okay, so before we move on, so we'll do an example of this, but there's another point that I want to bring. Percentiles are very useful in helping us determine what we need to get as far as a particular value, okay? So let's use SAT scores as an example. Let's say in the college arena. Let's say we have a particular college that only considers applications for admission for students who get within the 75th percentile. Okay? Well, what does that mean? Well, we can use the information, the 75th percentile, along with the mean and standard deviation to figure out what score represents the 75th percentile, or the cutoff, okay? So let's say I find out in the admission that this college only accepts SAT scores that are at the 75th percentile or higher, okay? Well, then my question is, well, what's the minimum score I need, right? So what's the cutoff? What score, what SAT score represents the 75th percentile? If I can figure out that score, then I know what I need to get, or the minimum I need to get on the SAT score to even qualify for admissions into that college. Does that make sense? Okay. So that's a perfect example of where percentiles help us determine values, okay? So, now, percentiles are usually used with large populations. You would not use percentiles for small samples or small sample percentages, okay? Let's see here. So let's look at this frequency table. So I'm going to construct this frequency table, and then we're going to use it to decide percentiles. Okay, so this is one way of doing it. Okay, so we'll start off with this table. Okay, actually, let me do this. See if I have another better marker. Start over here. Okay. So now we have this table here. And it doesn't really help. See if I can get. Okay, so let's say we're talking about hours of sleep. And here's our frequency. Here's relative frequency and cumulative relative frequency. Okay, so let's say this is our situation. Okay, so let me fill in these numbers real quick. So here's the hours of sleep. We'll go 4 to 10. Okay, so 4, 5, 6, 7, 8, 9, 10. Okay, so here's the table. So here is the situation, right? So here's the frequency table with the relative frequency and cumulative relative frequencies, okay? So here's our x values, right? So here's our x values for our table. And then we've got our 3 different types of frequency that we can look at. So frequency, relative frequency, and cumulative relative frequency, okay? So now here's the thing. Now we can use the definition of percentiles and to tell us some information about where people lie. Okay, so what if I wanted to know the 50% mark? Okay, where or the 50th percentile, right? So the value that represents the exact middle, the median, right? So if I look at my values here, remember, let's use the definition percentile. It's the value that represents where 50 or that represents that percentage of values that fall at or below that number. Okay, so let's say I wanted to find out where the 50th percentile is. So how many hours of sleep represents the 50th percentile, where 50% of the values fall below that, 50% of the values fall above that. So the median, right? The 50th percentile is also the median. Okay? So now, if I look at this, now this is where these two columns really aren't going to help us. I mean, we could use this column, but this is where cumulative relative frequency is key. Because here, the cumulative relative frequency actually tells us what percentage of the data falls below that value, at or below. That's the percentile. So you can look at cumulative relative frequency as the percentiles, right? So where would the 50th percentile lie? Well, look at this. This represents 52%, which is close enough, right? So we could say, hey, 7 hours of sleep represents the 50th percentile. So the median. So we could say, hey, the median amount of sleep that people get is about 7 hours of sleep a night. Okay? Or 7 hours of sleep represents the 50th percentile. So if you get 7 hours of sleep, you're in the 50th percentile. What if you get 8 hours of sleep? What percentile are you in now? Well, let's look at the table. Well, here's 8. Let's go to the cumulative relative frequency. What is it? 80%, which means what percentile does 8 hours of sleep mean? It means that if you get 8 hours of sleep, you are in the 80th percentile, which means that 80% of the people out there, right, based on this study, get as many or fewer hours of sleep than you do, okay, or less than 8. Okay? Any questions about that? Good. Good. I hope that makes sense. So this is one way you could use percentiles, right? Looking at a table like this, a cumulative relative frequency table. Okay? Okay. So let's look at some more. So we want to find the third quartile. Let's talk about well, do I want to? No, I don't want to talk about that because we're going to get into that later. So let's say, okay, so we did the median, we talked about that. Okay, so let's find the formula. So let's talk about the formula of calculating a percentile. Okay, so now this is, what if we were given data, okay, or a frequency histogram? So we're going to talk about formulas that actually tell you the kth percentile, okay? So we're using, so far all we've done is use the definition, which was easy enough. Now we're going to actually show you the formula that you could use to get you the answer. Okay. Okay, so let's do this. Let's erase this, because I don't think we're going to use this. Okay, so good. And if you use it again, you can just reference it in your notes. Hopefully you wrote all this down, if you needed to. Okay, so now, here is the formula for finding the kth percentile. Okay, so how do you find the kth percentile? Again, we're going to use I. Okay? So I is going to tell us the position. Okay, just like before we talked about finding the median of a data set. We order the data and then we find the ith position of the median. Well, we're going to use a similar formula for a percentile. Okay, so again, all we're going to think about the definition of a percentile. It's where that percentage of values falls at or below the given value. Okay, keep that in mind. Okay, so here's the formula. So I equals K divided by 100 times n plus 1. Okay. So let me explain how this works. Okay. Now, you can use frequency distributions, but there's several formulas out there, but I'm going to stick to the one that's in this text. Okay. So here's one of them. So if we want the kth percentile, it may not be part of the data. It could be part of the data, just like, again, with the median when we talked about before. Okay? So let n represent the total sample size, just like before. So that should be clear to us at this point. So n is the sample size, and I is the index, or that tells us the position we need to count to. Okay? For the percentile. And k is the percentile we're looking for. Okay? So if we want to know, hey, I want to know what percentile or where the position is for a certain percentile, then I plug in my percentile in for k. I plug in my value for the sample size, and basically look what I'm doing. I mean, think about it this way. What am I doing? It's out of 100, right? So what is a percentile? A percentile is 1 to 99, right? So what am I doing? I'm taking a proportion, right? I'm taking the sample size plus 1. So I'm basically taking the sample size and I'm finding what proportion of the sample size needs to fall at or below that value, right? And then once I know that, I is going to tell me how many I need to count, or how many of the data values in my sample size I need to make sure is below. Okay, so again, this works much easier when the data is ordered, right? Because then I can just cut it off and easily, and I can find where the percentile is. Okay. So again, I'm going to do an example. So here's an example. Oh, by the way, there's a couple of cases here. So, because I can be a positive integer, or it may have a decimal. Okay? So here's case 1. And again, this is just one way of looking at it. If you go on YouTube or if you do a Google search, you will find other formulas that work exactly the same way but are applied differently. Okay, just a different algorithm. So in this case, this is 1. Sometimes there's formulas that use n, okay, but the way they treat I is differently. Okay, so again, we're just going to stick with this. So if I is a positive integer, so I is a positive integer. Okay. Then there's really all you have to do, that's all you're going to do is you're just going to count to that position, just like we did with median. So, I'll do this. So, count to that position. And by the way, The one difference between dealing with this and when we find the median is with the way you count does where you start in your order data does matter. You have to start with the smallest and then count up to that position. So as before, when I said with median, you could count from either direction. Well, the only reason that is because you're finding the middle. So it doesn't matter which end you start with. But since we're dealing with percentiles, it does matter. So you always start with the minimum value and work up towards the greatest value. So you always work in increasing order. Okay? So you count to that position in the data. And that value is, or that value represents that percentile. That value represents given percentile. Or, you know what I should say, represents the kth percentile, since we're using k. Represents the kth percentile, or piece of k. Okay, again, you could denote it just piece of k. Okay? The reason why we use k is because we're using n for sample size, so I don't want to use n for here. It would just be confusing. So k is what we're going to use for the percentile. Okay, so that's case one. Okay, so now what if it's not a positive integer? Let's say if it's not a whole number. Okay, so in that case, what is it going to look like? Well, let's do case two. So it's not a positive integer, which means it's a decimal. Well, what are we going to do then? Okay, so case two is excuse me, is not a positive integer. Okay, well, then what I'm going to do is I'm going to round down and round up. Okay, so round up to nearest integer and find the data value. To that position. And then, of course, you can just take, if you're going to round up, then think of it just like we did with the median. This is where, if it's not a whole number, you're going to round up and you're going to round down, and you're going to find the data values in the ordered data that correspond to those positions, and then just take the average of them. That's basically what we're doing. So you could just round up to the nearest integer, right, and then get that one, and then take the one before it. Or you could round down to the nearest integer, find that data value, and then take the next one. Okay, that's basically what you need to do. I'm going to write both, both of them, but again, use it however works best for you. Okay, whatever makes sense to you. Okay, so we're going to round up to the nearest integer, find the data value in the ordered data that corresponds to that position, and then round down to find the other one. So round down to nearest integer, And then 3, average those two data sets, or average those two data values, I should say. So then just average the two values from the data, okay? So that's what you would do is if you don't get a nice whole number for I, okay? So those are the two cases you have to consider, and I hope that makes sense. So to help make it make sense to you, let's do an example. And so this example is going to require data. So I'm going to write down the data, and then what I'm going to do is I'm going to apply the formula to find the value that represents a particular percentile. Okay, so that's what I'm going to do. So let's write down the data value. So here are the list of ages. Again, so these are ages of 29 Academy Award winners for Best Actor. In fact, I think we may have used this data before, but I'm going to write it down. So again, just again, write it on your own notes or whatever helps you, but these are ages. So I'm writing down the 29 ages of Academy Award winners for Best Actors. Okay, so I'm going to write these down. Let me move over. So let me start over here. And these are already ordered, so that's good. This will be easy to see.